So what we discussed so far is when we have a pair of electron in the sigma orbital and it is now donated to the metal center, what we talk about the sigma donor ligand. So we get so many examples starting from the carbon monoxide, nitrosyl, hydrogen, hydride, and phosphorus, N-nitrocyclic carbon, all belongs to a category called the sigma donor ligand. Now we are going to talk about the pi donor ligand. And if you take up the simplest pi donor ligand is the ethylene molecule where you have a carbon, single bond carbon, sorry, carbon carbon double bond. If you consider one bond as a sigma bond, other one is a pi bond. Let's say this is sigma bond and pi bond. And if you talk about the energy level, the sigma bond, the pi bond, and then N, and then we have a pi star, and then you have a sigma star will be there. If you see, there is a pi bond which is relatively low in energy, relatively high in energy, and if they have a lone pair of electron, if that is donated to the metal center and making a sigma bond, again see, so only pi donor ligand because the electrons are present in the pi orbital, which is now donated to the metal center to form a sigma bond. Even though it is donating a pair of electron from the pi orbital, the metal ligand formation is only the sigma bond, and that is what we talk about here. So each double bond will have a pair of electron from the one pi bond. When you're moving from double bond to triple bond alkyne, you have again it's again there are two pi bonds will be there, but only one will be donated depending upon. So therefore, the one double bond sigma bond and pi bond, one double bond will consider as a L type of ligand and will contribute two electron. If you have more than one pi electron, we have a the number of electrons will be keep on increasing. That is what we discovered. And if you remember correct, the first ever reported compound, the Z salt, is actually a pi donor ligand. It's actually the Z salt, where you have a ethylene molecule is actually coordinated to the metal center. Therefore, the first ever example reported as an organometallic compound itself, it's a pi donor ligand. It's a Z salt. It's containing an ethylene molecule as the ligand. Okay, when we started discussing about the bonding, look at here. This is what we talk about the pi bonding. You have an electron present in the pi orbital, and that will be actually involving with the metal to form the sigma bond, corresponding sigma bond, and you have and you can see the pi electron which will be donated to the metal center to form the to form the sigma bond, and then you have a empty pi star orbital which is actually acting as the accepting orbital, the pi accepting orbital. Therefore all the pi donor ligand especially involving the double bond are all a very good pi accepting ligand because you could able to see an empty pi star orbital is present. Therefore that can be utilized to make the bonding, the pi bonding. Therefore not only on the basis of the metal carbon, but also the bonding ability in donate a pair of electron and accepting the electron density. Therefore, the ethylene molecule or any olefin containing organic moiety can be called as the organometallic compound. This is what the bonding. The another interesting aspect is that these olefin can adapt a two different type of model. One we say it is a Dewar chat model where it is a very simple straightforward ethylene molecule. We have a double bond in which we have a pair of electron which will be donated to the metal center to form a very simple standard pi electron donated to the metal center to form a sigma bond. This is we talk about the DCC model, Dewar chart Duncanson model. On the other hand, see, look at here. If you have this kind of bonding, and because of the coordination, the metal density will be keep on increasing. And ethylene molecule, you have a suitable pi star orbital. Therefore, metal started to give back the electron density to the carbon atom of the olefin. Therefore, I'm keep on adding more and more electron density on the anti-pi bond orbital. Therefore, what will happen at one particular stage? Almost the carbon-carbon double bond became single, almost close to the single bond. Therefore, it will adapt a kind of a different model called MCP model, metallocyclopropane model. Therefore, so when you talk about the the metal olefin complexes, it can have a two different type of mode of coordination. One will be talking about the Dewar Duncan chat model, DCD model, Dewar chat Duncanson model, or other one we talk about the MCP model, and how to identify which will be existing again because of the pi back bonding. Look at here, this is what I'm talking about, the pi back bonding, because you're dumping more and more electron density in the anti-pi bonding orbital. As the electron density in the anti-bonding orbital increases, the carbon-carbon double bond will weaken, and one particular time it is almost close to the carbon-carbon single bond. That is, we talk about the metallocycle propane model. But this is what we talk about the DCD model and the MCP model. But to be frank, we have to say none of the complex will have 100% like this kind of model or 100% like the model. Only the comparative nature are only a kind of what I can say. It is not 100%. Any of the molecule will not have a 100% DCD model because all the molecule accept the pi electron. All the olefin molecule, all the double bond molecule will accept the olefin. Therefore, there will be a considerable amount of MCP character will also be there. At the same time, it is not actually about the two electron, because only if you add two electron, then electron to the pi star orbital, we could able to reduce the bond order by one. Therefore, none of the complex will have exactly MCP model. It's about the percentage. What is the actual percentage? Some cases you may see a 90% DCD model, 10 percentage what I'm talking about the MCP model. On the other hand, if you may also have a 90 percentage MCP model and 10 percentage DCD model will be there. Therefore, never a complex containing an olefin ligand will have either DCD model or MCP model. It is always in between. It is always in between, and therefore what we actually will be doing it that we will say if the majority is dominated by the pi back bonding. The pi back bonding is poor, then the majority will be the geometry adapted by the olefin will be the DCD model, where the simple bonding, as the pi back bonding towards olefin is more greater than to the compared to the other ligand, and therefore we could be able to see they adapt the MCP model. So that is what we talk about. None of the, that's what say, this is what the first line says. You can hear the extreme experimental structures can fall anywhere between the two extremes. Never going to be the MCP model exactly or DCD model exactly. It's always in between the two one. Okay, so basically when you could able to expect, when you could able to expect MCP model, எப்போ ஒரு MCP model நீங்க நினைக்கிறீங்க pi back bonding will be more. எப்போ pi back bonding more இருக்கும் in case of olefin? எப்போ ஒரு ஒலிஃபின் வந்து அதிகமான பை பேக் ஃபண்டிங் ஆர் ஐ வில் அக்செப்ட் தி மோர் அமௌண்ட் ஆஃப் எலக்ட்ரான் டென்சிட்டி ஃப்ரம் தி மெட்டல், எப்போ எனக்கு எதிர்பார்க்குறீங்க? கொஸ்டின் புரியுதாப்பா?
சப்ஸ்டிட்யூன்ஸ் பொறுத்தா
சப்ஸ்டிட்யூன்ஸ், எந்த மாதிரி சப்ஸ்டிட்யூன்ஸ் இருந்தா ஒலிஃபின்ல வந்துட்டு பை பேக் ஃபண்டிங் அதிகமா இருக்கும்? எலக்ட்ரான் ரிலீசிங் குரூப்பா, எலக்ட்ரான் வித்ட்ராயிங் குரூப்பா?
எலக்ட்ரான் டொனேட்டிங் குரூப்
எலக்ட்ரான் டொனேட்டிங் குரூப் எலக்ட்ரான் டொனேட்டிங் குரூப் இருந்தா இல்லதம்மா, எலக்ட்ரான் டொனேட்டிங் குரூப் இருந்தா பை பேக் பண்ணி கூடுமா குறையுமா? எலக்ட்ரான் டொனேட்டிங் குரூப் olefin இருந்துச்சுன்னா பை பேக் பாண்டிங், the acceptance of electron density by the olefin will be more or less?
more.
less, sir.
Less, exactly. That is what the correct answer. Okay, I think she's told wrongly. So when you have a electron releasing group on the olefin, the electron is already electron rich. Sorry, the olefin is already electron rich, and therefore it won't accept any more electron density from the metal. Therefore, they tend to adapt the MCP model. Sorry, the DCD model. So most of the cases with the olefin with the electron releasing group like O-methoxy methyl tend to adapt the DCD model. On the other hand, if I'm substituting the hydrogen atom with the cyanide, the tetracyanoethylene or electron withdrawing group, Therefore, what will happen? The olefin actually electron deficient, and therefore they tend to make they ready to accept the electron density from the metal. Therefore, it will adapt the MCP model. That's what. Therefore, the electron withdrawing substitute on olefin lowers the energy level of pi star orbital and favor the pi back bonding and favors the MCP structure. Therefore, the electron density. When you talk about the requirement for a metal complex to adapt MCP model, what we need is the first 2 points should be the olefin should be electron deficient. It should be attached with the electron deficient. What are the other factor where it will the olefin or this metal olefin will adapt a MCP model? வேற எந்த கேஸ்லாம் மெட்டல் வந்து எப்படிலாம் இருந்தா மெட்டல்ல MCP கேரக்டர் அதிகமா இருக்கும். மெட்டல் சைக்ளோப்ரோபைன் மாடல் அடாப்ட் பண்ணும் olefin மீது. ஒன்னு வந்து எலக்ட்ரான் ஒலிஃபின்ல வந்து எலக்ட்ரான் வித்ட்ராயிங் குரூப் இருக்கணும். வேற கேஸ்ல வேற எப்படி பார்க்கணும்? வாட் ஷுட் பி தி மெட்டல் கேரக்டர்? இந்த மெட்டல் எப்படி இருந்தா பை பேக் பாண்டிங் அதிகமா இருக்கணும்?
Electron rich, sir.
Electron rich. Therefore, there should be in the lower oxidation state. That should be so. Therefore, metal should be in the lower oxidation. Therefore, the pi back bonding will be more, and therefore the pi back bonding will be more. The MCP model will be adapting. What else? வேற என்ன parameter இருக்கலாம்? வேற என்ன parameter இருக்கலாம்? Metal electron rich இருக்கணும். Olefin வந்து electron deficient. வேற?
Charge on the
what are the
metal
other
complex,
things? See, charge on the metal complex directly correspond to the metal oxidation state, directly corresponding to the electron density. So, அப்ப அது நம்ம எப்படி டிஸ்கஸ் பண்ணியாச்சு இல்லையா? வேற என்ன ஃபேக்டர்? What are the other factor?
Presence of pi acceptor or pi donor ligand other than alkene, sir.
Exactly. See here we don't have a complex simply metal and olefin. We may have other ligands also attaching. So the other ligands are attaching. Therefore, if a metal attached with a pi accepting ligand like carbon monoxide, nitrosyl, and therefore when you compare the carbon monoxide, nitrosyl, your olefin is a poor pi accepting ligand. Therefore, metal will tend to take will send the electron density towards the carbon monoxide, nitrosyl. Therefore, it will send very less amount of electron density to the olefin. Therefore, they will adapt DCD model. And therefore, the presence of electron donating, the presence of pi accepting ligand, strong pi accepting ligand will actually favors the pi back bonding towards the ligand, and therefore very less pi back bonding towards the olefin. Therefore, they will adapt the the DCD model. My question is that if in case your metal is now attached with a strong fluorine ligand like the CF3, or you can also have a CF3. So you have a difluorine, ரெண்டு fluorine atom attach ஆயிருக்கு மெட்டலோட, ஒரு trifluoromethylene group attach ஆயிருக்கு. Now what will happen? Where the pi back bonding will goes off. Pi back bonding எங்க இருக்கும்? அந்த olefin வந்துட்டு என்ன மாடல் அடாப்ட் பண்ணுவாங்க? DCD மாடலா, MCP மாடலா? If in case the other way general கேட்கணும் அப்படின்னா, when the metal is attached with the strong electron withdrawing group, what will happen to the what will happen to the structure of metal olefin? Whether they will adapt the MCP model or DCD model. இது அடாப்ட் பண்ணோம். இந்த மாதிரி இருந்ததுன்னா fluorine CF3 இருந்துச்சுன்னா pi back bonding எந்த பக்கம் இருக்கும்? Towards the fluorine or towards the olefin?
Sir,
Any guess?
DCD model, sir, towards olefin, towards fluorine, sir.
Why towards fluorine? How you are saying? What's the reason, Pa?
Sir, I don't know where the back donation is, sir, but back donation is little less to olefin, sir.
Why? That's what I think. Why back bonding is little less?
Because fluorine is more electronegative, sir, so it attracts the electron towards itself, so it doesn't allow the metal to donate the back donate it to the olefin, sir.
Correct. This is where everybody will make a mistake. So what we actually are speaking is the pi back bonding. See, the model either MCP or DCD is actually considered by the pi, how the ligand going to accept the ligand. When you consider the fluorine, when you consider the trifluorofluorine, they are not at all pi accepting ligand. Therefore, their nature is to only donate the pair of electron to the metal. They may delay. They may delay in giving a pair of electron to the metal. Therefore, that is the only thing happen. But once the pair of electron on the fluorine or CF3 is donated to the metal center, the metal become large electron density, and that is why the metal fluorine metal CF3 bond will be forming. Therefore, now you have a huge amount of electron density over the metal. Now the metal looks to dilute the electron density over them. Therefore, it looks for a suitable ligand to accept the pair of electron. Definitely your fluorine, definitely your trifluorofluorine, not at all going to accept any pair of electron, because the fluorine CF3 are not at all a pi accepting ligand. Therefore, all the excess electron density will go to the olefin. Therefore, it will only adapt the MCP model. Therefore, the majority of the electron density will go to the olefin, and thereby the MCP model will adapt. Therefore, see, remember there are two factors we actually always confusing. The ligand is pi accepting, and the presence of electron withdrawing group on that ligand. The presence of electron withdrawing group on that ligand will make the ligand to be better pi acceptor. But as such, if you talk about simple fluorine, simple cyanide, simple trifluoroethylene, all are a strong, all are a, what I can say, all are a highly electronegative atom, or kind of kindly electron withdrawing group, but they don't have any accepting ability. They cannot accept electron. Only thing, they will be reluctant. They will be reluctant to giving the pair of electron because of the electronegativity and because of the electron. The affinity. Therefore, but once they make the complex, the pair of electron density is donated to the metal center, and therefore, what will actually happen? The metal will become electron density. Therefore, it will tend to send the back electron density suitable orbital, and therefore, the olefin will be the suitable orbital. Therefore, the pi back bonding will be more. Therefore, it will have the NCP model. எல்லாருமே கன்ஃபியூஸ் ஆகிக்கணும். Remember, எலக்ட்ரான் வித்ட்ராயிங் குரூப் எங்க இருக்கணும் அப்படின்னா ஒரு லிகாண்ட்ல இருக்கணும். அந்த லிகாண்டுக்கு பை அக்செப்ட் இருக்கணும். அப்பதான் வந்துட்டு தி பை பேக் பாண்டிங் டுவோர்ட்ஸ் தி ஒலிஃபின் வில் பி மோர். அப்படி இல்ல, மெட்டலோட டைரக்ட் அட்டாச் இருக்கு, ஒரு ஃப்ளூரின் ஒரு குளோரின் அட்டாச் இருக்குன்னா there is no pi back bonding because fluoride chloride are not at all a pi accepting ligand. Therefore, nothing will happen. They will act as a simple ligand and donate a pair of electron to the metal center. That's it. There is no other job. It cannot accept the electron density. Even if you're putting cyanide, even if they're fluorine all have a highly electron withdrawing group and nature, they cannot take the electron density from the metal through pi back bonding. Therefore, their duty is to only to donate a pair of electron, and therefore the excess electron density only going to the olefin. Therefore, if the electron withdrawing group or the electron, what I can say, the electronegative atom attached to the metal, the pi back bonding always go to the olefin, not to the fluoride or trifluoroethylene. Is that clear?
Yes, sir. Clear, sir. Now I understand clear, sir.
So this way always people will confuse fluorines are electron withdrawing nature. So electron density will come to the metal. It is not the organic chemistry where we are talking about the electronegativity factor. It is the pi back bonding. What we need is the suitable orbital. Your simple fluoride or cyanide doesn't have any very good pi accepting ligand. Therefore, the electron density will go only to olefin. That's the interesting point you have to know. So if we talk about the pi back bonding, when I'm talking about the DCD model, the pi back bonding towards olefin will be minimum, and carbon-carbon double bond. Since the pi back bonding is minimum, the carbon-carbon bond order not 2, but it is greater than 1.5. Greater than 1.5 because the pi back bonding is less, therefore only less electron density go to the pi starter. Therefore, the bond order will be not exactly 2, but it is close to 1.5 to 2. And charge on the vinyl carbon is always going to be the delta positive because the electron density is less there. And then the hybridization, because it is almost carbon-carbon double bond, therefore they will remain as a sp2 and will be in the plane. More in generally, the metal oxidation state will be kind of an intermediate. It's not very high or not very low. On the other hand, if you talk about the metallocyclopropane model, MCP model, the bond order, because of the pi back bonding from metal to olefin is larger, therefore the bond order greatly decreased from 2 to close to 1. Not exactly 1, not exactly 2, but it may be between 1 to 1.5, indicating the longer bond distance between the carbon and carbon. And if you see the
of the pi back bonding is more and more on the carbon, therefore carbon will have a delta negative charge. And what I'm talking about is the second factor is the hybridization. Since the almost carbon-carbon double bond is collapsed, it is supposed to having a sp3, nearly sp3 hybridization, and most of the cases the metal will have a very low oxidation state because then only the pi back bonding will be higher. This is what the bonding nature. And the another interesting aspect about stability. See, stability, and I can ask you a small question, which will be more stable. If I just give an example, you have a platinum attached with a CH2 double bond CH2 simple olefin, or if it is attached with the, like say PP double bond with a tetra, I will put a methyl Me2 and C Me2, which will be more stable. The tetramethyl ethylene containing platinum complex or tetraethylene or we simply ethylene complex, which will be more stable. Platinum with only ethylene group or platinum with a tetramethylene ethylene ligand, tetramethyl ethylene ligand, which will be more stable. Platinum with a simple ethylene, or we have a tetra. I'll put a simply I will say tetra substituted olefin. This is ரொம்ப stable இருக்க முடியும். Olefin tetra substitution. Stability means what I'm talking about when there is an incoming ligand is coming, which will be reactive more. The simple ethylene or tetra substituted ethylene.
Sir, ethylene
will be
ethylene, sir.
Ethylene will be
reactive, sir.
Reactive. Therefore, they are not stable. Why?
Sir, tetra substitute and bulky organa ligand incoming ligand approach பண்ண முடியாது, sir.
Exactly the same reason. Okay, don't think about anything like what I'm talking about, the pi back bonding, DCD, MC model. They are only bonding, and they are all thermodynamically stable. No problem with that one. Whether it is an MC model or DCD model, they are thermodynamically stable. And the reactivity, what actually affect is actually the size. That's what the order says. You could hear. Look at here, the stability defines that your tetra substitute ethylene, is actually more stable because in case of an olefin, when you replace all hydrogen atom with a methyl or ethyl or any group, what will happen? The size, the bulkiness of the ligand increases. The bulkiness of the ligand increases. Therefore, if I'm trying to knock out one of the ligand, the incoming ligand go and attack the metal center. But because of the steric nature, the incoming ligand do not have the ability to go and attack the metal center. Therefore, they became more stable. Or let's say they will react very less, or it takes more than 24 hours to do the reaction. If you have a tri-substitute one, from tetra to tri-substitute, at least one position you have a small hydrogen atom to which your incoming ligand can attack the metal center, and therefore the speed of the reaction will be more. And then the di-substituted, in the di-substitution you have a cis and trans. You can see trans will be more stable because because of the trans position, the incoming ligand cannot make a move freely either from one of the direction. Therefore, the trans orientation ligands are more stable than the cis, because cis means you either from the top or from the bottom, the incoming ligand can attack the metal center. They become very stable, and the last or the least stable is the non-substituted simple olefin. We talk about it. This is what we talk about. I think a couple of times the CSR asked this question in a different way, but everybody thought about something electron withdrawing group, electron releasing like that. But it is simply the substituents on the carbon atom. Substituting the carbon atom, which was found to be the least substituted carbon is more reactive, and the tetra substituted carbon is more stable. That's what we talk about. And when I say pi back bonding, the question may also comes with the carbon-carbon bond or the platinum-carbon bond. In your general opinion, which carbon-carbon bond strength will be very short in the MCP model or DCD model? MCP model bond strength, bond length, longer இருக்குமா இல்ல bond length வந்து weak இருக்கு, short இருக்குமா? எந்த மாடல், MCP or DCD? MCP or DCD? Have the lowest carbon bond length, MCP or DCD? இதுல ரொம்ப என்னப்பா?
Bond length will be higher in MCP model.
Exactly. In MCP model, bond length will be higher because it's close to carbon-carbon single bond. Other the carbon-carbon double bond will be in DCD model the carbon is actually let's say carbon-carbon double bond. Therefore, the bond stronger. Therefore, the bond distance will be smaller. And one more factor which will have a strong metal carbon in DCD model and MCP model. Strong metal carbon bond. Metal carbon. The MCP or DCD?
MCP, sir.
MCP. Why? Besides the normal coordination, there is some pi back bonding. Through the pi back bonding, the metal interacts with the carbon. Therefore, you are right. The metal carbon present in the MCP model will be higher. Therefore, the question can be of anything. Whether you can ask which will be have a MCP model, which have DCD model, or discuss about the which is have a long arrange them in the carbon-carbon bond distance or metal carbon distance bond. What your thought process would be the pi back bonding. Where the pi back bonding goes, that's why I said most of the question, if you think about the pi back bonding, you could readily answer it. Okay, and this is a question the CSR asked already.
சார் இப்போ கைனடிக் ஸ்டெபிலிட்டி ஆர்டர் பார்த்தோம்ல சார், அது தெர்மோடைனமிக் ஸ்டெபிலிட்டி ரிவர்ஸ் ஆர்டரா இருக்குமா சார்?
Thermodynamically stability கேட்டீங்கன்னா thermodynamically tetra substitute compound will be more stable than means it's not going any reactivity.
சார் அது கைனடிக் ஸ்டெபிலிட்டி தானே சார், அது நியூக்ளியோஃபைல் அட்டாக் பண்ணும்போது அது பல்கினஸ் வச்சு ப்ரிவென்ட் பண்ணுது. தெர்மோடைனமிக்னா
பல்கினஸ் இருக்கறனால உங்களுக்கு எப்படி சொல்றது, பல்கினஸ் இருந்தாலும் காம்பவுண்ட் ஸ்டேபிள் தானே இருக்கு. See, at that case, you need to talk about the energetic level. Maybe you can talk about the on the steric interaction energetically less, therefore less stable. Thermodynamically, the compound stable, we could be able to store it and keep it because it's an organometallic compound. Because it is obeying the 18 electron rule. Therefore, thermodynamically, they are stable.
ஆனா வந்து டெட்ரா சப்ஸ்டிட்யூட்டோட அந்த சப்ஸ்டிடியூஷன் இல்லாத எத்திலீன் தானே சார் பாண்ட் ஸ்ட்ரென்த் நல்லா இருக்கும் மெட்டலோட.
இல்லையே, நீங்க இப்படி பாருங்களேன். See, when you have the hydrogen atoms are replaced with a cyanide group, it became tetracyanoethylene. Therefore, tetra substitute one, the pi back bonding will be more, or metal carbon bond will be stronger because of the pi back bonding.
அப்ப தெர்மல் ஸ்டெபிலிட்டிக்கும் பை பேக் பாண்டிங் நம்ம ரிலேட் பண்ணலாமா சார்?
பண்ண முடியாதுல்ல, தெர்மோஸ்டெபிலிட்டிக்கும் பண்ண வேண்டிய அவசியம் கிடையாது. See, what you are trying to say, thermodynamic stability na the compound exists or not exist, adna
yes sir, reaction illama just on the compound
I could able to store it. All the cyanide, all the olefin compounds I could able to store it. If I remember correct, I tell you the story. நான் சொல்லிப்பேன் நினைக்கிறேன். அது ஆக்சுவலா அந்த Z salt is an actually accidental discovery. அவங்க ஒரு எலக்ட்ரோ கெமிஸ்ட்ரி பண்ணும்போது using platinum salts, ethanol molecule எல்லாம் போட்டு தான் பண்ணாங்க. It formed the platinum, it formed the olefin complex. அப்போ அந்த இடத்துல CH2 double bond CH2 தான் இருக்கு. They are also more stable. அது ரொம்ப ஸ்டேபிளா தான் இருக்கு. It is not that நீங்க இல்ல thermodynamic stability நீங்க சரி thermodynamic stability all the compounds are thermodynamically stable. நீங்க கேக்குற அடுத்த கேள்வி thermally stable கேட்டீங்கன்னா we can start discussing. Thermodynamically stable means எல்லா compound I could able to prepare, I could able to store it, including olefin compound, tetra substitute olefin compound could able to prepare and stable. And நான் பாட் கூட என்ன சொல்ல பண்ணிக்க முடியும். But if you ask me the question thermal stability, something called thermal stability, then thermal stability upon increasing the temperature. Now heat increase பண்ண the molecule randomly move will be faster, therefore the steric interaction will be less. ஏன்னா அங்க molecule move ஆகும்போது sterically they are bulk, therefore they collide each other, therefore they will be decomposed. Whereas the small ethylene ligand, not tetraethylene, simple olefin ligand will be thermodynamically also more stable.
ஓகே சார், அப்ப தெர்மல் ஸ்டெபிலிட்டி மட்டும் தான் ரிவர்ஸ் ஆர்டர் வருமா சார்?
தெர்மல் ஸ்டெபிலிட்டினா ரிவர்ஸ் ஆர்டர் சொல்லிக்கலாம்.
ஓகே,
தெர்மோடைனமிக் ஸ்டேபிள்னா எவ்ரிதிங் இஸ் ஸ்டேபிள்.
ஓகே சார்.
Thermodynamic stable means whether I could able to make the compound and I could able to store it. Yes, I could able to store it. all the compound we could able to prepare and we could able to store in, and depending upon nature, it has to be maintained as the nitrogen atmosphere or the other atmosphere. அவ்வளவுதான் அதுக்கப்புறம் தெர்மலி ஸ்டேபிள் சொன்னாதான் நீங்க சொல்ற அந்த ஸ்டெரிக் ஃபேக்டர் மூலமா ரிவர்ஸ் வரும். Okay.
Okay, sir. Thanks.
Okay. So this is the actual question. This is the question. This is the three compound they actually given the CSRSN and ask you to arrange in the carbon-carbon bond distance. The carbon-carbon bond distance. This is the question asked. Here, I just say it's a very interesting question. That is, wherever I go, I will always say the four important parameter. Whenever you see a metal complex, you have to see the metal oxidation state, number of the electron, and the number and the coordination number and the total valence electron. In this case, if you just look at the complex, everything looks like platinum complex. But if you closely look at, there is a change in the oxidation state. The first compound is platinum plus 2, other compounds are platinum 0. But this will be not given in the question paper. In the question paper, you are given only with the complexes. Therefore, what I said, whenever you see a complex, you find the oxidation state, number of the electron, the coordination number, and the total valence, and then you can answer the question like this. If you could able to see the complex one is in plus 2, other two are plus 2, higher the oxidation state, what could be the pi back bonding? Pi back bonding அதிகமா இருக்குமா கம்மியா இருக்குமா? என்னப்பா?
கம்மியா இருக்கும்
higher the கம்மியா இருக்கும். Therefore the pi back bonding will be poor. Therefore carbon-carbon bond strength will be stronger. Therefore carbon-carbon bond strength will carbon-carbon bond distance will be shorter. The shortest one is 1.37 angstrom. And then you come to the another compound where both are in platinum 0. Now the metals have a platinum 0, therefore they will have an equal amount of electron density. Now we have to look at the pi back bonding. Where the pi back bonding going? Whether to the hydrogen atom or to the tetracyanoethylene. The higher the pi back bonding, more will be the electron withdrawing group present in the pi donating pi in the ligand. Pi accepting ligand, it actually act as a more pi accepting ligand. Therefore, in case of tetracyanide, there will be more pi accepting ligand, and therefore the pi back bond will be more. Therefore, platinum carbon bond will be stronger. Carbon carbon bond become weaker, and this will have the longest or weakest carbon carbon bond around 1.49 angstrom. Where this is the middle, neither doesn't have a strong, neither doesn't have a weak. It is actually in between, and therefore we could able to see the order will be the platinum 2 will have the longest, shortest, and then the platinum 0 with the ethylene, and then platinum 0 with the tetracyanethylene, and that is the answer. Is it clear? புரியுதாப்பா? ஓகே ஃபைன். ஸோ இப்போ இந்த 3 காம்பவுண்டுமே கொடுத்து இதுல எது எம்சிபின்னு சொல்ல முடியுமா, எது டிசின்னு சொல்ல முடியுமா, இல்லை எப்படி கம்பேர் பண்ண முடியும்? வாட் யுவர் தாட் அபவுட் இட்? இந்த 3 காம்பவுண்டை கொடுத்துட்டு இதுல எது எம்சிபி மாடல் எது டிசி மாடல் சொல்ல முடியுமா உங்களால? கரெக்டா ஒன்று மட்டும் பிக் பண்ண சொல்லலாங்கண்ணா. டு யூ திங்க் இஸ் இட் பாசிபிள்? எது எம்சிபி எது டிசி? Yeah, that's what the question. Okay, so if there is a comparison of 3 compound, it is not that much easy to pick whether it is MCP model or DCD model, or the comparison always with the 2 molecule. If I'm comparing only the first and 2, which will be the MCP model? 1 and 2, which will have the MCP model?
Second one.
Second one. Okay, second one is called MCP model, and this is DCD model. But if I'm comparing the 2 and 3, which is MCP model? Obviously, the second one is the MCP model. This first one is actually a DCD model. Therefore, it's all related to them. Therefore, it is also written. What we can do is that only we can able to arrange them in the increasing nature of MCP. Again, talking about the carbon-carbon double bond or carbon-carbon single bond. Well, platinum with the 0 oxidation state and tetracyano being more pi accepting, they will have a higher percentage of MCP model, and therefore the carbon-carbon bond distance will be longer or weaker, or I can say the carbon-carbon bond distance will be weaker. On the other hand, the platinum plus 2, relatively, they have a very poor pi accepting, therefore they tend to adopt the DCD model. The nature will be more towards the DCD model, whereas even though chlorine, chlorine attached to the metal center. Chlorine as an individual element, electron withdrawing group, but as a ligand, it is not a pi accepting ligand. It is not the pi accepting ligand. It is only a sigma donor ligand, donates the pair of electron and won't accept any electron density from the metal center. Therefore, the first compound can have a higher percentage of the DCD model, which will be reflecting in the carbon-carbon double bond, the shortest and strongest bond. Therefore, we have to be a bit careful about the classification. Is that clear? புரியுதாப்பா? Can
Yes,
we move
sir.
forward? Yeah, fine. Yeah. So this is what we talked. The same thing again in a simple schematic way. Given it here. Okay. What happened? You can talk about the triple bond. The same, it could adapt either it could adapt the DCD model or a MCP model. Here MCP propene, cyclopropene model, and this is we talk about the DCD model, the same kind of thing. The pi back bonding. Where the pi back bonding going? If the pi back bonding towards olefin is more, they will adapt the MCP, the cyclopropene model. Whereas the pi back bonding going to the other ligand or the pi back bond is relatively less. Therefore, it is called as the DCD model. The same strategy can also be adapted for a carbon-carbon triple bond. Okay, so we start with a single bond. Now I am going to add one more number to that one. We have a C3 and it's a negative charge. So it is a type of an LX type. What I'm talking about the ligand, allyl ligand or vinyl ligand. This is we talk about vinyl ligand. So therefore, as per the counting system, this is a 2 electron donor and the negative is 1 electron. Therefore, this ligand is actually a 3 electron and donor. There are so many complexes have been reported. There are so many complexes reported, and these complexes are very much interesting. It will behave in a two different mode of coordination, either through the hapticity 1, where only one carbon atom is coordinated to the metal center, or through the hapticity 3, where you can see able to see all the 3 carbon atoms are coordinating. So in this case, it is a 1 electron donor, and in this case, it's a 3 electron donor. So these are a highly flexible ligand. I will say these are a highly flexible ligand. The formula is 1. The formula is C3H5. But it can act as a hapticity 1 ligand, it can act as a hapticity 3 ligand. It is a 1 electron donor, it is a 3 electron donor. Therefore, if we can say, depending upon the requirement, depending upon the requirement of the metal, the allyl ligand or the allyl ligand, we could able to form either it can act as a 1 electron donor ligand or a 3 electron donor ligand. இந்த மாதிரி வேற ஏதாவது flexible ligand நமக்கு படிச்சுக்குமா இது வரைக்கும்? So unlike C3H5 is one example where it could able to adapt a two different mode of coordination. One one either it is in hapticity 1 mode or hapticity 3. Both the cases is a terminal. It is not like a bridging or something. வேற ஏதாவது கேஸ்ல மோட் ஆஃப் கோஆர்டினேஷன் சேஞ்ச் ஆகாம எலக்ட்ரானை மட்டும் சேஞ்ச் பண்ண முடியுமா? ஏதாவது லிகாண்ட் இருக்கா? நாட் தி மோட் ஆஃப் கோஆர்டினேஷன், அந்த பிரிட்ஜிங் இந்த மாதிரி இல்லாம ஒரே மோட் ஆஃப் கோஆர்டினேஷன், பட் அதுக்குள்ள வந்துட்டு டிஃப்ரெண்ட் டைப் ஆஃப் எலக்ட்ரான் வாங்க படிச்சிருக்குமா?
Nitrosyl.
Exactly, nitrosyl. Nitrosyl actually will have a 3 electron donor and 1 electron. Both are actually in terminal. The terminal mode of coordination, your nitrosyl is a 3 electron donor and the bent is a 1 electron donor, and that is also a flexible ligand, and this is also a flexible ligand. When you talk about the bonding, how this kind of allyl system will be forming, again you have a allyl system, there is a 1 double bond, therefore there is a pair of electron present in the pi orbital, and because of the negative charge, it is actually present in non-bonding orbital of the pi orbital. All the 3 electron will be donated to the metal center to form the hapticity 3 ligand, or at least only 1 electron can be donated to the metal center to form a hapticity 1. Therefore, it is forming a metal ligand sigma bond will be forming. Once the sigma bond is formed, the metal will have a huge amount of electron density. They will look for to transfer the excess electron density, and you have a empty pi star orbital. Therefore, the allyl, the hapticity 1 or hapticity 3, both the way it is a strong sigma pi donor ligand. and a very good pi accepting ligand, and therefore it is a very good interesting ligand. So what the main interesting aspect is that depending upon ரொம்ப self adjustable ligand, யார் வந்தாலும் help பண்றதுக்கு ரெடியா இருக்க மாதிரி. Look at the reaction. You have a sodium MnCO5 upon reacting with the allyl chloride. So initially the sodium chloride lost, because of the loss in the only one electron, because of the loss, the charge lost only one minus. This MnCO5 mighty already have a 17 electron. It just need only one electron. Therefore, considering the situation, your C3H5 ligand will adapt the hapticity one mode of coordination, and therefore 17 plus 1 18 rule. Therefore, it is actually forming the hapticity one. When I'm heating the reaction, what will happen? One of the carbon monoxide core leading to formation of MnCO only 4 times, which is actually a 15 electron system. Therefore, this compound is actually looking for a 3 more electron. In that case, the same C3H5 ligand will adapt the hapticity 3 form and forming the 18 electron complex. Therefore, depending upon the requirement of the metal, this kind of allyl system may adapt a hapticity 1 or hapticity 3 ligand, and therefore it is a highly flexible ligand, I will say. Is it clear? About the allyl system. When we moving from a 3 electron donor to the 4 electron donor, you have something called a butadiene. In the butadiene, you have a two different two pi bonds are there. Each pi bond will have a pair of electron in the pi orbital, and therefore they could be able to donate to the metal center. And look at the MO diagram. You have the HOMO levels. This is, we talk about the pi orbital, pi 1 and pi 2. Both are, you have a lone pair of electron which can be donated to the metal to form a sigma bonding. And you can see there is an empty pi star orbital through which the metal can send back the electron density to the orbital, and therefore we could be able to make. Therefore, the butadiene is actually a very interesting ligand, and it can act as a pi donor ligand as well as the pi accepting ligand. Is it clear? அப்ப நான் என்ன பண்ணலாம், அப்படியே எக்ஸ்ட்ரா பார்ட் பண்ணலாம். அடுத்து என்ன வரும்? லீனியர் பென்டாடைனேல். லீனியர் பென்டாடைனா இப்படி இருக்கும். So we have a kind of இது butadiene, and then you have a CH2 minus. Now this is L type, this is another L type, this is X type. Therefore, it is a L2X type of ligand. It can contribute 2 electron, and 1 electron, and therefore it is a 5 electron donor. Like this, அப்ப என்ன ஆகுனா ஒரு நான் பாண்ட் எலக்ட்ரான் இருக்கும். அந்த நான் பாண்ட் எலக்ட்ரான் மூலமா it can give only 1 electron, it can give 2 double bonds, therefore it can give only Therefore, it can give only 2 plus 1, 3 electron, or only 2 electron can be given, or combining the other orbital also 2 plus 2 plus 1 equal to 5 electron, depending on the requirement, the ligands will be easily adjusted. And then if I keep on increasing one more member, I will get the 1, 3, 5 hexatriene, where 6 carbon atom with a 3 double bond. I can just add it, and the very polyclear we get the same correlations can be carried out. This is about the linear molecule containing a pi bond, like heptene, hexene, like that. Keep on adding, we will get the thing. Now what we'll do, we'll put a cyclic system. These first two, comparatively a stable cyclic system is the cyclobutadiene. Cyclobutadiene. Do you think organically cyclobutadiene is stable or unstable? Cyclobutadiene stable இருக்குமா unstable இருக்குமா? Cyclobutadiene.
Unstable.
Why it is unstable? ஏமா? It's actually unstable. It's not it's unstable, correct. It's unstable. Why it is unstable?
It's anti-aromatic.
It is anti-aromatic. It has only it has only the less number. It is not obeying the four-knuckle rule. It is the planarity. Planarity is there, but it's not obeying the rule. Therefore, it is actually a kind of it's not a stable compound. Immediately, the ring will be open up and forming the kind of a monomeric unit will be forming. Therefore, it is very, very difficult to stabilize the cyclobutadiene. நீங்க போயிட்டு கேட்லாக் எடுத்து செக் பண்ணி பார்த்தீங்கன்னா cyclobutadiene கிடைக்கவே கிடைக்காது. Cyclobutadiene கிடைக்கவே கிடைக்காது because they are not that much stable. But At the same time, when I'm treating the cyclobutadiene metal center, I could able to stabilize. Look at here, in both the cases, you could able to see a cyclobutadiene ligand is there without any substitution. இந்த இது மாதிரி இல்லாம cyclobutadiene இருக்கு. How it is possible? இன்ஆர்கானிக் நான் ஆர்கானிக் காம்பவுண்டா வச்சா எனக்கு ஸ்டேபிள் இருக்க மாட்டேங்குது. நான் இன்ஆர்கானிக் காம்பவுண்ட் வச்சா ஸ்டேபிள். அது என்ன காரணமா இருக்க முடியும்? How the unstable or unstable anti-aromatic cyclobutadiene as an organic compound, they are unstable, but the very much same compound which is very much stable when it is coordinated with the metal center. Why and how? எப்படிப்பா எப்படி இந்த காம்பவுண்ட் ஸ்டேபிளா இருக்கு? Could you able to see any difference? சொல்லுங்கப்பா.
18 electron அப்படியே சார்.
ஆர்கனோமெட்டாலிக் காம்பவுண்டுக்கு 18 எலக்ட்ரான் வேணும் இல்லையா? அது ஓகே, அதனால ஆர்கனோமெட்டாலிக் காம்பவுண்ட் சொல்றேன். பட் ஒரு we need to talk about ஆர்கானிக் லிகாண்ட் தான். When you say benzene as a ஒரு ஆர்கானிக் மாலிகுலா, அது ஆர்கானிக் மாலிகுல் தான். அது இன்ஆர்கானிக்ல கோஆர்டினேட் ஆனாலும் அது பேர் பென்சின் தான். இப்ப 18 எலக்ட்ரான்ங்கிறது அந்த காம்பவுண்ட் ஸ்டெபிலிட்டி. நான் கேட்கறது ஒரு ஆர்கானிக் காம்பவுண்டா ஒரு லிகாண்டா சைக்ளோபியூட்டடைன் அன்ஸ்டேபிள். பட் அதே எப்படியோ நான் கஷ்டப்பட்டு மெட்டலோட ரியாக்ட் பண்ண வச்சுட்டேன்னா அந்த சைக்ளோபியூட்டடைன் அப்படியே டெரிவேட்டிவ் அப்படியே இருக்கு. என்ன காரணம்?
பை பேக் பாண்டிங்.
எப்படி பை பேக் பாண்டிங்? அதனால என்ன வந்துருச்சு? கரெக்ட் தான். சி அதான் சொல்ல, என்ன கேள்வி எப்படி கேட்டாலும் நீங்க வந்து ஈஸியா பை பேக் பாண்டிங் சொல்லலாம். பட் எப்படி?
அதனால அரோமேட்டிசிட்டி அட்டைன் பண்ணுதா சார்?
Exactly. That is what the difference. Look at the structure I have written here and the complex. In the complex, I have put a cyclic form, meaning that electron ring current is there. அப்போ aromatic ஒரு cyclobutadiene இருந்து அது எப்படியாவது cyclobutadienyl anion மாறுது. Because when you talk about the simple cyclobutadiene, it has only 4n electron. To attain this stability, what we need, Akul rule should be 4n plus 2. What is lacking in organic compound? Cyclobutadiene. Lacking in the cyclobutadiene is the 2 electron is a deficiency. And imagine now it is when it is coordinated with an iron or ruthenium 0 compound, the pi back bonding is given, and the amount of electron density transferred to the pi back bonding is almost equal to 2 electron. Almost equal to 2 electron, and that is the reason we are putting an aromatic current, and it is going to give a very stable cyclobutadiene moiety, and therefore they are stable. And now you could able to imagine, or it's like indirect evidence which could able to see there is a pi back bonding exists. A normal cyclobutadiene does not exist, or it is easily converted into the polymer, whereas when it is coordinated at the metal center, it nicely adapt a cyclopentadienyl moiety. How it is achievable? Because of the pi back bonding. And imagine that pi back bonding amount is equal to that of a 2 electron. Therefore, the pi back bonding exists, and actually only once Caesar also the same question. Is that clear? The pi back bonding in cyclobutadiene. So as we move from the cyclic system with the 2 pi bond, now there will be the next one will be the very interesting one, the cyclobutadienyl anion or C5H5 minus. This is the very stable compound, a very interesting organic moiety which is quite stable. This is aromatic cyclobutadienyl and it's an aromatic compound. It obeys all the rule, became highly aromatic, 4n plus also obeying, so there, so it's a very stable compound. And for a simple representation, we used to represent the cyclopentadienyl in many ways. Look at here, you have simply hapticity X, H5 summa போடுவோம், இல்லடி வெறும் CP just on the வெறும் CP போடுவோம் or hapticity. In case if you are saying simple CP, that is actually corresponds to hapticity. இல்ல வெறும் C5H5 அப்படினா you should take it as a hapticity 5. Only in case if they are giving hapticity 1, therefore it is actually only one carbon atom is called into the metal center. அப்ப கரெக்டா புரிஞ்சுக்கணும். அதே மாதிரி தான் CP ஸ்டார். What is the difference between CP and CP star is the all the hydrogen atoms are now replaced with the methyl group. Look at here, this is C5 Me5. இங்க இருந்து C5 H5. அவ்வளவுதான். இந்த ரெண்டுனால என்ன அட்வான்டேஜ் வந்துருப்போது நமக்கு? ஏன் ரெண்டு தனித்தனியா படிக்கணும்? ஏன் ரெண்டையுமே பண்றாங்க? ஏன் C5 சில இடத்துல C5 H5 யூஸ் பண்றாங்க, சில இடத்துல C5 Me5 யூஸ் பண்றாங்க. அப்ப என்ன ஏதோ இருக்கு இல்லையா? சம்திங் இஸ் தேர். What are the special property or what are the difference between CP and CP star? CP star na C5 methyl 5. So நானே இங்க வச்சது தப்பு. It should be Me5. சொல்லுங்கப்பா, என்ன டிஃபரன்ஸ் இருக்கும் ஒரு சிபிக்கும் ஒரு சிபி ஸ்டாருக்கு? என்ன டிஃபரன்ஸ் இருக்கு? வாட் இஸ் தி டிஃபரன்ஸ்? என்ன டிஃபரன்ஸ் சிபிக்கும் சிபி ஸ்டாருக்கும்? Size small in case of CP, size is bulkier CP star, and therefore in order to stabilize some unstable compound, I always take CP star. So for example, some of metal center does not react with the CP to give a very stable compound, immediately decompose. In that case, being a smaller size, the reactivity will be higher. Therefore, I can increase the ligand bulkiness by substituting the hydrogen with the methyl group. Therefore, I could be able to do the reaction. I could be able to isolate. இது ஒரு காரணம். Steric hindrance. I could be able to make a play around the steric hindrance. What else? வேற என்ன பார்க்க முடியும்? வேற என்ன advantage?
எலக்ட்ரான் டென்சிட்டி இன்க்ரீஸ் பண்ணும் சார்.
எலக்ட்ரான் டென்சிட்டி. ஓகே, அதனால என்ன இம்பாக்ட் ஆக போகுது? எலக்ட்ரான் டென்சிட்டி இம்பாக்ட் ஆகிறதுனால என்ன 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 மாற போகுது? பிகாஸ் ஆஃப் தி 5 methyl group, அதனால என்ன இம்பாக்ட் ஆக போகுது?
பாண்டிங் பிட்வீன் தி மெட்டல்
எப்படி 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 இன்க்ரீஸ் ஆகுமா டிக்ரீஸ் ஆகுமா? பாண்டிங் பிட்வீன் தி மெட்டல் இன்க்ரீஸ் ஆகுமா டிக்ரீஸ் ஆகுமா?
இன்க்ரீஸ் ஆகும்.
எப்படி இன்க்ரீஸ் ஆகும்? See, the compound will be more stable only if you have a strong pi accepting ligand. அதுதான் இம்பாக்ட். Okay, so let's skip that point. One point begin. The other interesting advantage is the replacing hydrogen with the methyl group. The solubility increases. The solubility increases because you are moving from hydrogen atom to a methyl group. Therefore, you could expect higher solubility for the CP star containing metal complex. Because if you keep on going, the complex stability also, as we keep on going for the higher element or heavier mass element, the solubility usually decreases. Therefore, to make it soluble, what we'll do, we actually replace the hydrogen with the methyl group. That is what we talk about the thing. That is what this fixes. And then you can see the CP star are strong pi accepting here. That is correct, but it's not because of the it is not because of the methyl group. If you have a methyl group, there should be a poor pi acceptor. Now, actually, imagine you have a cyclopentadienyl anion. In order to stabilize the ring current, C5H5, I need to have a more electron releasing group. That's the reason you see the C5 Me5, all the 5 methyl group are now attached with the CH3 group, CCH3 group. And what will happen? They will stabilize the negative charge. They will stabilize the negative charge. Therefore, they could be able to give the electron density. And because of this stabilization, the anti-bonding pi star orbital will be less in energy, and therefore they can really accept the electron density from the metal. And this is what here, nothing to do with the electron releasing group. If it is an electron releasing group, that ligand should be a strong, a poor pi accepting ligand. But இங்க என்ன சொல்றோம்? CP star is a strong pi accepting ligand. என்ன காரணம் அப்படின்னா, the 5 methyl group in the CP star is actually to maintain it's actually to maintain the charge. அங்க ஒரு சார்ஜ் இருக்கு, அந்த சார்ஜ் காம்பன்சேட் பண்றது தான் 5 methyl group இருக்கு. And during the process, the pi star energy level will be reduced, and now It will now Python is going to I can nicely do the pi back. The metal can nicely do the pi back bonding, and that is what happening. The CP star ligands are most interestingly the very good pi accepting ligand. And if there are two CP rings are present in a metal, they tend to have a eclipsed or tend to have a staggered conformation. Most of the cases, the staggered conformation is said to be more stable, and because of the less electron density repulsion. But that is not true for all the cases. It depends upon it depends upon the molecule we are dealing with. The gaseous molecule, you have this kind of eclipsed conformation is more stable. But the solid and solution state, what we need is the staggered conformation is more stable, and that is what we talk about. Yeah, this is what these are. So these kind of using the cyclopentadiene ligand, we could be able to make a three different kind of complexes can be formed. One is the CP2M, what we talk about the metallocene compound, where metallocene has sandwich compound. You can see the cyclopentadienyl group acting as a bread. Or sandwich மேலையும் கீழையும் bread இருக்கும். Stuffing like that. You have in the top and bottom you have the cyclopentadienyl, and in between you have a metal. Therefore it is called as a sandwich compound. This is one type of set will come. The other one, and the other one is the tilted sandwich or bent metallocene complexes or bent metallocene. So in this case, if you look at, there are two cyclopentadienyl ligands there. As in the previous case, there are two cyclopentadienyl will be present. But along with the two cyclopentadienyl, you have some other ligands also. But in this case, only CP2. That's it. There are some other ligands also, but it's called the CP. That talk about the bent metallocene. And the other difference is right. In addition to that one, you have other. The angle. When you talk about the CP nickel CP, the bond angle is close to 180. But if you have a tilted, the CP, CO, and then another carbon, it only 130 to 120 to 130, and therefore they are called as the bent metallocene. The third one is the half sandwich compound, meaning that only one CP ring will be present, will be attached to the other ligand. We talk about the half sandwich compound, okay? Therefore, using CP, we could be able to make three different type of compound: the sandwich compound, the bent metallocene, and the half sandwich compound. So in this case, here is another interesting. That's what I'm talking for. I always say there are only three concepts: the 18 electron rule and the pi back bonding system, and then the MO diagram. The third concept. This MO diagram kind of approach should be applicable only to the sandwich compound. Whereas your half sandwich and your bent metallocene all will adapt the 18 electron system and the pi back bonding. Therefore, if you are given with a system and asked to compare, first of all, you should be able to differentiate whether it is an organometallic compound. Whether it is an organometallic compound. If it is an organometallic compound, if it is currently a cyclic system, therefore it will form the bent metallocene or the linear metallocene, bent metallocene or half sandwich compound, or a full sandwich compound will be forming. How to distinguish? That is more important, because sometimes your metal attached only with the CP ligand. Along with the CP ligand, some ligands are possible like C1 or thing. And third one, only one CP ring will be there. In this case, only the sandwich compound, only the first category, the sandwich compound, we need to follow the third concept. We need to follow the third concept. Whereas the bent metallocene and the mono and the sandwich, half sandwich compound, always we need to consider only on the 18 electron rule and pi back bonding. We can treat normally as a simple organic compound. But for the sandwich compound, your approach should be different. You take in terms of the molecular orbital approach. For that one, the first ever stable compound reported using cyclopentadiene is the ferrocene. And this is the one compound which was very well thoroughly exploited and understand the basic mechanism all this using for an example for the sandwich compound. The sandwich compound, the eclipse to form where the CP ligands are in the exact plane, whereas in this agate in the form it is actually tilted. And this is what we talk about. And when you want to discuss, this is what the great interest idea develops here. How to describe the bonding? How to describe the bonding between the cyclopentadienyl and iron? People initially thought it is an ionic compound. It's an ionic compound like you have a Fe plus 2, you have a 2 CP ligand compared with the FeCl2. If it is an ionic compound, it should be highly soluble in water or high polar solvent. But what is the interesting factor with the CP2 is that it is only soluble in hexane, indicating the non-covalent, indicating more covalent nature or non-ionic form. Therefore, how it can explain? நம்ம எதிர்பார்க்கிற ஒண்ணா இருக்கு, அங்க வேற மாதிரி ரிசல்ட்டா இருக்கு அப்படின்னு எதிர்பார்க்காங்க. They also talk about as the lower the zero ion is in zero compound and you have a cyclopentane சொல்றாங்க. But அதுக்கும் ruled out ஆயிருது because it has so many other parameters. அப்ப என்னதான் எக்ஸ்பிளைன் பண்ணா we need to go only the MO diagram. We need to go with the MO diagram where you could able to see there are 9 orbitals are present in the metal complex. The valence orbital, the orbital coming from the metal S, E and D orbital, 9 orbital, and you have another 10 orbital coming from the two cyclopentane again, each carry a 5 carbon 5 carbon. Therefore, the total atomic orbital available is 10 plus 9 equal to 19. The total atomic orbital available will be 19 orbital will be there. And out of 19 orbital, 19 orbital 8 are bonding orbital, 10 are anti-bonding orbital, and 1 is a kind of a non-bonding molecular orbital. So the 3 different type of things are forming, and we know that if it is a bonding metal orbital, it should occupy with the electron, and if it is anti-bonding orbital, you should not have the electron. If it is a non-bonded orbital, you could able to put the electron. On that basis, look at the MO diagram. Look at the diagram. This is a bit complicated. You don't need to worry about the thing. This is the orbital. This is about the just a minute. This is about the outermost orbital, which contribute 9, and there are 10 orbitals from the ligand because 10 carbon atom. And then what is actually happening is the electron. We have iron. Iron is a D6 system. Iron plus 2 is a D6 system, and you have this carbon electron. So we combine. That's what will happen. We are going to start fill up the electron. Look at here, bonding orbital, non-bonding orbital, and anti-bonding orbital. And look at here. I have done. There is one excess electron density which is actually occupied the non-bonding orbital. Non-bonding orbital. That is the thing. Okay, and this is the MO diagram. And as I said, you don't need to memorize the complete period table. What you remember is that, and what was a scientific fact also, the 8 bond. If you go and closely analyze the orbital, these remaining, let's say, the low energetic the 10 orbital is actually have a more characteristic of ligand, and the anti-bonding orbitals are corresponding to the anti-bonding orbital, and these are all have a more d orbital nature. Therefore, we out of 19 atomic orbital, we can classify them into an 8 and 6, I suppose 8 and 6. Yeah, 8 and 5. So now we need to fill the electron. Therefore, what will happen? Your CP ligand is actually 6 electron. நம்ம வந்து திருப்பம் பேசிக்கா போனோம்னா நம்ம வந்து நம்ம பண்ற அந்த கால்குலேஷன் மெத்தட் தப்பு. That is only to count the number of electron. The actual electron contributed by the CP minus is 6 electron donor. எப்படி 2 pi bond இருக்கும், அது போக ஒரு நெகட்டிவ் சார்ஜ் இருக்கும். Therefore it is 2 plus 2 plus 2 equal to 6 electron. Therefore 1 CP is actually a 12 electron. The 12 electrons should be filled with the lowest bonding orbital, and then whatever the electron present in the metal should be placed here. the metal should be placed here. Therefore, indirectly it is saying that the valence orbital is actually have the characteristic nature of the metal. And you remember that the valence orbital is actually responsible for all the properties of the complex. Therefore, simply by drawing the MO diagram and just consider only the number of electrons in the metal orbital corresponding is D1, D2, D3 system, we could able to predict the property. And that is what I think. Yeah. So look here. This was the many of Petrosian properties are actually based on the valence orbital. Therefore, you can look at here. And this is therefore, if you remember that this is the hemodiagram for ferrocene, and this is the in between where it actually have a very strong metal interaction will be there. Sorry, actually have the phi orbital actually decides the parameter. Therefore, it is not necessary to memorize the full complete period table. You just remember only this the frontier orbital, because the frontier orbital electron actually deciding the chemical and physical properties of the compound. Therefore, we have to remember and look at here. This is how it is actually written as. In the bottom you have a two same energetic orbital, the middle one, and then in the top you have an anti-bonding. This is anti-bonding orbital, this is the non-bonding orbital, this is the bonding orbital. These are the three different way we could be able to get it. And this is not that much important, you can skip it. So, and therefore what we need to remember is that you find the oxidation state and fill the number of electrons. That is more than sufficient. You could be able to get all the answer. Okay, and remember in this case of ferrocene, the cyclopentadienyl ligand, the last two, the bottom one and the middle one, they actually have almost same energy. Therefore, they can be written as 1, 1, 1. But correct order கீழ ரெண்டு மேல ஒன்னு அதுக்கப்புறம் ரெண்டு. We talk about the E2G, M1G and E1G. Yeah, this is not that much important. And then now you have to study the individual one. Almost all at least the 3D element, it actually form a very stable sandwich compound, except the two metal. One is scandium, which is very difficult to prepare, and titanium being larger in size, they tend to not to form a very stable sandwich compound. Rather, it is mostly forming a kind of a bent metallocene, the bent metallocene will be forming. Other than that, starting from vanadium, chromium, manganese, iron, cobalt, nickel, all will actually forming a sandwich compound. Okay, and all these sandwich compound actually forming a low spin complex. What is low spin complex? Even if you have a pair of electron here, it should be filled and then it's go to the next level. If you have any other orbital is empty, we cannot go directly. We have to completely fill the orbital and then we have to go. So therefore, your sandwich compound, all these sandwich compound will actually form a kind of a low spin complex, except only one, manganese. Manganese plus 2 is the only compound. Manganese plus is only one compound which will adapt two different type of thing. One is called low spin complex, other one is called high spin complex. One is called low spin, we have other one high spin. அப்ப எப்ப இந்த manganese high spin மாறும், எப்ப manganese வந்து low spin மாறுனா, when manganese plus 2 it attaches with the mesitylene. When manganese, not mesitylene, when you have a manganese form the complex with the Cp star, this actually Cp star manganese, Cp star twice manganese. It actually this compound is tend to be more stable, and your manganese is the only element which could be able to form both the high spin and low spin complex. Simple Cp will adapt the high spin complex, whereas Cp star is actually forming a low spin complex. Low spin complexes it will be developing. All other elements nicely form all the stuff. That is not a big problem, and this is what they think. And this is also so let's take an example of vanadium Cp2. What is the total valence electron in vanadium Cp2? எவ்வளோப்பா total electron எவ்வளோப்பா vanadium Cp2 ல? Vanadium Cp2. What? 15. Okay. Do you think the compound is stable?
Sir,
The compound.
13.
என்னப்பா கேட்கல.
வெனடியம் +2 ல
கேட்கலப்பா.
இருக்கலாம் சார். 13 தானே சார் வரும்.
சரி. இங்க தான் நீங்க பண்றீங்க. See, when you're talking about the calculation of total valence electron, we normally don't consider the oxidation state. Therefore, we have to assume that metal in zero oxidation state. Therefore, 5 plus 10 equal to 15. நீங்க ஆக்சிடேஷன் ஸ்டேட்டை கன்சிடர் பண்ணீங்கன்னா வெனடியம் +2 அப்படின்னா it will have 3 electron. கரெக்ட் தான் D3. But your cyclopentadiene is a 6 electron donor. That's the same answer. 6 plus 6 plus 3 equal to 15.
ஓகே சார்.
Both are, it is 15 electron தான், ஒன்றும் பிரச்சனை இல்லை. I'm asking the question whether the compound will be stable, thermodynamically stable. The compound stable இல்லையா?
18 எலக்ட்ரான் ஒபே பண்ணல சார்.
ஒபே பண்ணல. But this compound is stable, but this is a sandwich compound. Sandwich compound not necessary obey the 8 electron rule. அதான் சொன்னேன் இல்லையா, சாண்ட்விச் காம்பவுண்ட்னாலே நம்ம இந்த எமோடைரம் வச்சு பண்ணா போதும். அங்க 8 எலக்ட்ரான் ரூலும் அப்ளை கிடையாது, அங்க எதுவுமே கிடையாது. இப்ப வெனடியம் Cp2 is highly desirable. We could able to prepare and store it, indicating they are stable compound, thermodynamically stable compound. If you are asking for the kinetic stability, I will say no, vanadium Cp2 will be highly reactive. But thermodynamically stable, yes, it is thermodynamically stable. I could be able to prepare, I could be able to store it. I am thermodynamically stable, and therefore, what could be the oxidation state of vanadium here? In the vanadium oxidation state,
+2 சார்.
+2. Therefore, number of d electron is
3 சார்.
3. So, அப்ப என்ன ஃபார்ம் ஆகணும்? It's a 3 electron. அப்ப then you have to put the MO diagram. MO diagram எப்படி போடணும்? கீழே 2 ஆர்பிட்டால், மேல ஒரு ஆர்பிட்டால், அதுக்கப்புறம் ஒரு ஆர்பிட்டால். But this energy level between the EG and A1G are almost same. Therefore, we have to fill the electron like 1, 2, 3. The number of unpaired electron present in the vanadium Cp2 is 3 unpaired electron, and therefore 3, which is actually equal to the magnetic moment equal to 3.87. The magnetic moment equal to 3.87. And you look at here, this is my theoretical calculated value 3.87. What is the reported value? 3.84. How close it is. And the bond order is, it is actually the number of unpaired electron is 3 minus 0 divided by 2 equal to 1.5, and that is what we talk about. The bond pi is 1.5. அப்ப மெட்டலோசின் அப்படின்னு மெட்டலோசின்னா சாண்ட்விச் காம்பவுண்ட் அப்படின்னா சைக்ளோபென்டாடைன் மட்டும்தான் லிகாண்டா இருக்கணும், ஒரே ஒரு மெட்டல் இருக்கணும். அதுக்கு பேர் தான் வந்துட்டு வி ஹேவ் மெட்டலோசின். அப்ப இந்த மாதிரி எமோ டயக்ராம் கண்டுபிடிச்சு தான் நம்ம எல்லா ப்ராப்பர்ட்டியும் நம்ம வந்து அக்செப்ட் பண்ணிக்கணும். லெட்ஸ் டேக் ஒன் மோர் எக்ஸாம்பிள் with respect to your CrCp2. What's the total valence electron? Total valence electron is 16 upper 6 plus 10 16. The oxidation state of chromium is plus 2 or plus 3. CrCp2 oxidation upper. I'm getting it. Plus 2. Plus 2 electron. Chromium plus 2 is a D4 system. So D4 system we could able to write in two different way. 1, 2, 3, 4. இப்படி எழுதலாம். 1, 2, 3, 4. This is called the low spin compound. All your metallosin compound will form only low spin compound except manganese. But in the case of chromium, the form of number of unpaired electron is 1. Therefore, the answer is 1. Number of 2. Therefore, the answer is 2.83, which is correspond to magnetic correlation of 3.2, and the bond order became 2. Bond order equal to number of electron present in the bonding orbital minus the number of electron present in the anti-bonding orbital. Okay, the மாதிரி பார்க்கலாம். Again, Mn is an interesting compound. Mn with the Cp. Mn in Cp form high spin complex. Mn with the Cp star will form low spin complex. இதுதான் ரொம்ப கேர்ஃபுல்லா நீங்க அனலைஸ் பண்ணணும். இப்போ இது MnCp2 இருக்கு. இது என்ன டைப் ஆஃப் காம்ப்ளெக்ஸ் ஆகும்? ஹை ஸ்பின்னா லோ ஸ்பின்னா? MnCp2
high spin sir.
high spin. MnCp2 star போட்டிருந்தா low spin complex. Okay, கரெக்டா பண்ணிடலாம். சேம் திங் we could able to find. இப்பதான் நம்ம ஒரு அடுத்த கொஸ்டின் ஒரு ஆன்சரே பண்றோம். என்ன ஆன்சர் பண்றோம் அப்படின்னா, if you remember correct, when I talk about the introduction about the organometallic compound, we said the ferrocene compound is more stable. Now you compare here, though it is a metallocene compound which do not obey the 8 electron rule, your ferrocene is obeying the 8 electron rule. And the bond order is the maximum 3, therefore they are highly stable. This is why we say ferrocene is a very stable compound. நான் சொல்லி நினைக்கிறேன். இப்ப வாங்கி வச்சுட்டு ஒரு 50 வருஷம் கழிச்சு கூட பார்த்தா கூட ferrocene அப்படியே ferrocene மாதிரி இருக்கும், ரொம்ப ஸ்டேபிளா இருக்கும். That's not true with a simple organic compound. நீங்க ஒண்ணுமே கிடையாது, பென்சாலியில வாங்கி வச்சுட்டு ஒரு 2 மாசம் கழிச்சு வந்து பாருங்க, அது பென்சாயிக் ஆசிடமா இருக்கும், பாதிக்கு மேல சால்ட்டா இருக்கும். அளவுக்கு they are thermodynamically unstable, but this compound is very much stable, the ferrocene. Okay, look at here. இங்க எப்பவுமே ஒரு அடிக்கடி ஒரு கொஸ்டின் கேட்பேன். Look at here. When I'm crashing the iron, especially cobaltocene and niclocene, and also here you could be able to see the chromium and vanadium. In case of the cobalt and nickel, the electrons are filled up in the anti-bonding orbital, which is again corresponding to the bond order of 2.5. ஒரு MO diagramல bond order fraction வரலாமா வரக்கூடாதா? வந்தா என்னப்பா சொல்லணும், நம்ம ஃபிராக்ஷன் வந்தா
somewhere between 3 and 2 sir.
இல்லப்பா, கொஸ்டின் இதுதான். ஒரு எலக்ட்ரான்னா நீங்க ஆன்டி பாண்டிங் எலக்ட்ரான் போட முடியுமா? போடலாமா?
போடலாம் சார்.
அது எங்க போடுவீங்க? இப்ப நான் ஒரு டைஹைட்ரஜன் ஒரு மாலிக்யூல் கொடுக்குறேன், H2. அது ஒரு எலக்ட்ரான் நீங்க எங்க போடுவீங்க? H2 மைனஸ் கொடுக்குறேன். The 1 electron will go to the anti-bonding orbital. அப்ப bond order என்ன ஆகும்? 0.5 ஆயிரும். 0.5 ஆயிடுச்சுன்னா the molecule exists or does not exist? When you have a bond order in fraction, we normally say the molecule does not exist. Correct? நம்ம எவ்வளவு தான் சொல்லுவோம்?
Sir.
சொல்லுவோம். எதை நம்ம அப்படி சொல்லுவோம்ல? And on the other hand, if a molecular orbital or bonding orbital is not filled up with electron, நீங்க bonding orbitalல நீங்க கரெக்டா ஃபுல்லா எலக்ட்ரான் ஃபில் பண்ணா அந்த காம்பவுண்ட் does not exist தான். Look at your first two compound, vanadium and chromium. It is not completely filled with the bonding orbital. அப்ப அதெல்லாம் அன்ஸ்டேபிளா தான் இருக்கணும். Am I right? தடபா இது அன்ஸ்டேபிள் தான் இருக்கணும்.
கம்மியா தானே சார் இருக்கு.
பாண்ட் ஆர்டர் ஃபிராக்ஷன்ல வரக்கூடாது இல்ல, அதான் படிச்சிருக்கோம். ஆனா இங்க பாண்ட் ஆர்டர் ஃபிராக்ஷன்ல வருது. பாண்டிங் ஆர்பிட்டல் நீங்க ஃபிளிப் பண்ணா போடுறீங்க. உங்களுக்கு தெரியுமா கண்டிஷன்? தெரியல. MO டயகிராம்ல ஒரு பெரிய கண்டிஷன் இதுதான். என்ன கண்டிஷன்? பாண்டிங் ஆர்பிட்டல் should be completely filled. ஆன்டி பாண்டிங் ஆர்பிட்டல் should not be filled with electron. நான் பாண்டிங் எலக்ட்ரான்ல எலக்ட்ரான் இருந்தாலும் பிரச்சனை, இல்லாட்டியும் பிரச்சனை கிடையாது. தானே? அப்ப இங்க இடத்துல இப்படி அலோவ் பண்றோம். நம்ம இங்க பாண்ட் ஆர்டர் ஃபிராக்ஷன் இருந்தாலும் காம்பவுண்ட் வந்து ஸ்டேபிள் சொல்றோம். பாண்டிங் ஆர்பிட்டல் எலக்ட்ரான் கம்மியா போடுறோம், அப்போ பாண்ட் ஸ்டேபிள் சொல்றோம். என்ன காரணமா இருக்க முடியும்னு நினைக்கிறீங்க? என்ன காரணம்ப்பா? get me point? நான் சொல்றது உங்களுக்கு புரியுதா?
எஸ் சார்.
ஸோ இப்போதான் கிளாரிட்டி வரணும், சரிங்களா? நம்ம இது வரைக்கும் படிச்ச MO எங்க படிச்சோம் அப்படின்னா, we talk about the s-block element where the overlapping orbital is s and p orbital overlap. ஸோ s orbitalum p orbital எப்படி ஓவர்லாப் ஆகும்? ஸ்ட்ராங்கா, ஹெவியா, இன்டென்ஸா ஓவர்லாப் ஆகும். அப்போ அங்க வந்து இந்த MO diagram has to be strictly followed. meaning that bonding orbital completely fill இருக்கணும், anti bonding orbital electron இருக்கக்கூடாது, non bonding இருந்தாலும் கிடையாது. But here what I'm talking about is the d orbital. The involvement of d orbital, the overlap of d orbital with the ligand s and p orbital is not that much effective. Therefore, we say bonding orbital, but they are actually relatively not a lowest energy. We say that is something called an anti-bonding orbital. They are not actually really anti-bonding orbital. Therefore, the interaction here, the interaction is actually the d orbital, the d orbital, the the stability will be less. Therefore, we could able to have a bond order in the fraction. The bond order will be either fraction or putting a just a okay, is that clear?
Yes, sir.
Okay, so that is the reason. நம்ம அடுத்து இங்கே நம்ம இதே மாதிரி தான் உங்களுக்கு இங்கே வரும். ஹாலைட் கிளஸ்டர்லயும் பாண்ட் ஆர்டர் ஃபிராக்ஷன்ல வரையும் அப்பவும் என்ன சொல்லுவோம், பிகாஸ் ஆஃப் தி டி ஆர்பிட்டால் ஓவர்லாப் தான். சரிங்களா? ஸோ யா தட்ஸ் வாட் வி அதுதான். ஸோ பட் அது எப்படி இன்டைரக்டா உங்களுக்கு ரிஃப்ளெக்ட் ஆகுதுன்னா, லுக் அட் தி பாண்ட் லென்த். When you have the bonding orbital not completely filled, the bond length is longer, therefore weaker the bond. When you have a anti-bonding orbital, again the same, the bond order is longer. If you took exactly ferrocene where the bonding orbitals are completely filled and do not have a fraction bond order, that is the only case the metal carbon bond distance is very much stable, and that is why ferrocene is very much stable. Look at the bond distance is very short, and that is what is actually happening. This is what with respect to your the ferrocene. அப்ப இந்த மாதிரி எனி ferrocene இல்லையா, நீங்க எப்பவுமே இது வந்து ரொம்ப ஈஸி. ஸோ when you have a sandwich compound எப்படி இருக்கணும், மேல ஒரு சிபி கீழே ஒரு சிபி நடுவில் ஒரு மெட்டல் இருக்கணும். இது தான் we say sandwich compound. அப்படி இல்லை அப்படின்னா நம்ம ரெண்டு சிபி இருக்கு, இல்ல ஒரு சிபி இருக்கு, மத்த லிகான்ஸ் தான் இருக்கு, ரெண்டு சிபி லிகான் இருக்கு, மத்த லிகான்ஸ் தான் இருக்கு அப்படின்னா they are either the bent metallocene or we talk about the half sandwich compound. அந்த மாதிரி காம்பவுண்ட் எல்லாம் எங்க கொண்டு போயிடணும், they should be simply treated as a simple organic compound. You have to consider the 18 electron rule and the pi back bonding. But if you see any complex like this, the metallocene, then you have to draw the MO diagram, at least the frontier orbital diagram, and find the number of d electron and fill it up and get you will get the answer. ஏன் diamagnetic, ஏன் paramagnetic, எதுக்கு bond length ரொம்ப ஷார்ட்டா இருக்கும், எதுக்கு ரொம்ப ஸ்ட்ராங்கா இருக்கும், இந்த மாதிரி எல்லாமே உங்களுக்கு வந்து இதெல்லாம் நம்மளால டிஸ்கஸ் பண்ணிட முடியும். This is what we talk about the CP ligand. அப்ப பாருங்க இந்த question பாருங்க, out of these two compound which have a theoretical magnet, calculate the theoretical magnetic. Most of your organometallic compounds form low spin complex, they are paramagnetic, they are diamagnetic. But CP, the sandwich compound, may have an unpaired electron, may not have an unpaired electron. அப்ப அதெல்லாம் எப்படி கண்டுபிடிக்கணும்? First of all, you have to confirm that this is a sandwich compound. Sandwich compound எப்படி, ரெண்டு cyclopentadienyl ஒரு மெட்டல் இருக்கணும். அப்ப அடுத்து என்ன செய்யணும், we have to find the oxidation state of the metal. Here the oxidation of ion is +3, therefore d5 system. The number of d electron is actually d5, and fill it in the MO diagram. You could be able to see there is one unpaired electron is present, therefore the magnetic moment is square root of n into n plus 2 and 1.73. அதான் சொல்ல முடியும். அதே மாதிரி COCP2 minus, அது இல்லை நினைக்கிறேன், பட் COCP2 minusனா the cobalt is in -1 oxidation state, therefore it is a D8 system. D8 எப்படி fill பண்ணுவீங்க, you have to fill it like this: 1 2 3 4 5 6 7 8. There are two unpaired electrons are present, therefore the square root of n into n plus 2 and you will get the value. அந்த மாதிரி நம்மளால கண்டுபிடிக்க முடியும். This is the overall list if you want to. ஒரே ஒரு கேஸ் தான் manganese, we need to be careful. Manganese with the CP, it is forming a high spin complex. With the CP star, low spin complex. Other than that, you follow the same, you could be able to get it done. Is that fine? Be able to understand? புரியுதாப்பா? அப்ப எந்த இடத்துல எந்த கான்செப்ட் யூஸ் பண்ணீங்க தான் முக்கியமானது. இந்த சாண்ட்விச் காம்பவுண்ட் வரும்போது வேற யூ ஹேவ் ஒன் மெட்டல் ஆட்டம், 2 cyclopentadienyl, வேற எதுவுமே இருக்கக்கூடாது. no other ligand should be there. That is called a sandwich compound. அந்த மாதிரி கேஸ்க்கு இந்த MO diagram யூஸ் பண்ணி நம்ம clear ஆன்சர் கொண்டு வந்துடலாம். Okay, but half sandwich compound பாத்தீங்கன்னா all the half sandwich compound will follow strictly 18 electron rule. அங்க 17 19 இருந்தா compound unstable, exactly 18 இருந்தா மட்டும் தான் stable ஆக முடியும், and it will be applied to the pi back bonding. Pi back bonding complete apply ஆகும். Same with respect to the bent to metallurgiனுக்கும் இதே கேஸ் தான். அப்ப அந்த மாதிரி bent to metallurgiனுக்கும் sandwich compoundக்கும் we do not need to draw the MO diagram. அதை வச்சு நம்ம ப்ராப்பர்ட்டிஸ் கண்டுபிடிக்க வேண்டிய அவசியமே கிடையாது. You just looking at only the 18 electron and the pi back bonding amide. இதான் சொல்லியிருப்போம். ஓகேவா? When you move from cyclopentadiene, the next member will be the benzene. Benzene also nicely form a complex, but இங்க benzene அந்த அளவுக்கு ஸ்டேபிள் கிடையாது. They are not that much stable because after the donation, actually the ring current is reduced. Therefore, the benzene itself very weak. Therefore, the sandwich compound made out of benzene is not that much stable compared to your the ferrocene compound. And also, they always want to be ரெண்டு benzene இருந்துச்சுன்னா அது எப்பவுமே இந்த மாதிரி ஹாஃப் சாண்ட்விச்சா மாற ட்ரை பண்ணும், ஹாஃப் சாண்ட்விச் காம்பவுண்டா மாற ட்ரை பண்ணும். ஏன் அப்படின்னா most of the case is found that the even numbered benzene rings are not that much stable compared to the single one. That is what I discussed. And when you ask about the conformational analysis, at least in ferrocene we could able to have some clear cut idea. Solid state la vandu adu vandu eclipsed irukum, maybe gaseous state la vandu staggered conformation இருக்கும் நம்ம சொல்ல முடியும். No, reverse. Gaseous state வந்துட்டு eclipsed conformation, solid state வந்து staggered conformation. பட் இங்க அப்படி கிடையாது. Benzene can be of staggered conformation, can be of anything. அதுவும் நமக்கு ஒன்றும் பிரச்சனை கிடையாது. And if your benzene have some any electron withdrawing group, electron releasing group, again they are useless, nothing to do. They are not going to change any conformation. The conformation is not going to change. This benzene ligand will adopt its own conformation depending upon the other parameter, not depends on the metal, not depending upon the electron withdrawing, electron nature present in the benzene system. And when you want to describe the bonding, again you have to go with the MO diagram, where we have a 6 carbon atom or 6 atomic 6 plus 6 12 atomic orbital combined with the 9 combined with the 9 metal orbital to produce 9 bonding orbital, 12 anti-bonding orbital. And as usual, you need to focus only on the valence orbital, the T to G metal character orbital, because that is the one going to determine the property of the complex. Therefore, you don't need to memorize all the period table. You just remember the MO diagram of this one. This looks like very much same as that of your ferrocene. In one way it is different. The energy gap between them will be different, because therefore it should strictly follow the energy gap. If you have a D3 system, how you will fill? You will to fill 1, 2 and 3 here. This is for the benzene connecting system. But for a cyclopentadiene ligand, நம்ம எப்படி பண்ணிருப்போம் அப்படின்னா வந்துட்டு cyclopentadiene நம்ம எப்படி பண்ணிருப்போம்னா we have to fill, we'll say, though they are two different energy, but they are almost equal energy. For 1, 2, 3 important. This is for the CP containing sandwich compound. When you have a benzene containing sandwich compound, how you are going to fill the 3 electron? 1, 2, 3. Therefore, after completing the 4th electron only, the 5th electron occupies the d square orbital, and that is the only thing you need to be you have to be very much clear. Similar, these all are exactly same. And similar, take one example. What is the total valence electron? Titanium C6H6 twice. The valence electron hello, total valence electron. The total valence electron.
16. Sir.
Titanium 16. Okay. What is the oxidation state of titanium here?
0, sir.
The ox 0. Therefore, number of the electron is
4, sir.
D4. Okay. How to fill D4 அப்படின்னா இது benzene system. அப்ப இந்த எனர்ஜி கேப் ரொம்ப அதிகமா இருக்கும். அப்ப 1, 2, 3, 4 இப்படி தான் fill பண்ணனும். Therefore, you don't see any unpaired electron. Therefore, unpaired electron, sorry, I wrongly pressed. Just 1 minute. Discard பண்ணிடலாம். Just 1 minute. Discard, cancel. Just 1 minute. Go back. Yes. Play. I could be able to see the PowerPoint. Therefore, it doesn't have an unpaired electron. Therefore, the magnetic moment becomes, it's a diametric compound. Magnetic moment becomes 0. That is exactly happened. And the bond order is 4 minus 0 divided by 2. That is equal to 2. And vanadium, total valence electron is 17. The oxidation state of vanadium is 0. Therefore, it is a d5 system. Every other one electron, the one unpaired electron present in the orbital. Yeah, therefore, we have to take note, and you can the close matches the thing, and the bond order become 2.5. The bond order became 2.5. Similarly, here you could able to write all the stuff. You could be able to get it, and other contrasting with respect to the 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 cyclopentadienal is that whether you have a simple benzene ligand or you have a hexamethyl benzene, both always form only low spin complex. அது மேங்கனீஸா இருந்தாலும் சரி எப்படிதான் கிடையாது. All the benzene and hexamethyl benzene, they have to have the adapt the only form the low spin complex. Only in case of the cyclopentadienal ligand, the manganese depends upon the Cp or Cp star, it form the low or high spin. Manganese with the Cp forming a high spin complex. Manganese with the Cp star forming a low spin complex. பார்த்திருப்போம். அப்ப கிட்டத்தட்ட ஒண்ணுதான். அந்த எமோ டயராம்ல ஒரு சின்ன வேரியேஷன்ஸ் இருக்கும். We have to get it. And these are the examples for the for the uh, for the benzene containing complexes. One more high one will be tropylium ion. What could be the coordination number offered by tropylium? Possibly C7H7 plus. Tropylium is an example for L3X. அப்போ ஒரு ligand எத்தனை coordination number ஆட் பண்ணா 4 number. Therefore, being a smaller transition element, the sandwich compound of tropylium is not possible. ஏன்னா coordination number 4, மேலே 4, கீழே 4, 4 plus 4, 8. 8 coordination number is not possible for a small transition metal. Therefore, the tropylium ion never form a sandwich compound. Rather, they will always form simple mixed ligand compound. Therefore, we can simply treat them as a simple organometallic compound like the pi back bonding and the 18 electron rule. That is more than sufficient to be done here. And these are the example for the tropylium ion. And next high M will be cyclooctatetraene. Again, cyclooctatetraene simply says COT is not an aromatic compound because it doesn't obey the what I can say, doesn't obey the planarity, doesn't obey the accrued rule, and therefore they never coordinate with the complete all 4 coordinates is the L4 system. The complete L4 system is not possible because they are not enough. Therefore, some of them will not be available for making bonding. Either adapt hapticity 6, hapticity 4, hapticity 2, hapticity 2, and hapticity 1 and 3 can form. But in a single metal, it won't give a hapticity 8. It has the ability to form hapticity 8 through the 4 double bond. It has the ability to adapt hapticity 8. But it never form. It never form because of the size, because the transientals are smaller in size. Therefore, it cannot form a complete sandwich kind of compound. Other thing, okay. On the other hand, if I'm going for the other higher member, this is COT. Look at here. The structure is cyclooctatetradienyl anion. We talk about C8H2 minus. C8H2 minus, meaning that it is L4X2 single cyclooctadienyl. Single cyclooctatetradienyl anion itself contribute 6 coordination number. Therefore, it is very much impossible for a transition metal to make a complex. Therefore, you cannot see any COT containing a transition metal complex. Mostly, it will be it will be forming a complex with the F-block element, which we'll be discussing later, the F-block chemistry. And there is no 9-member ring. For some other example, there is no 10-member. The organic people have not developed a C10H10 or the 10-membered cyclic compound. But if they synthesize and we could be able to make an ferrocene isomer, either it could adapt a cyclic form or this form. This is only the hypothetical, just for your information, nothing to do with them. Okay. With only one ligand, other interesting ligand with respect to the organometal is the fullerene. This is the structure of the fullerene. Fullerene is actually an organic material, but it can nicely act as a ligand. And most of the cases, the fullerene, look at it, these are an example for a fullerene. Look at here, you have a platinum attached with the fullerene. You can see ruthenium attached to the fullerene. You can see the iridium. Yeah, you can see the iridium making a thing. And if you closely look at the fullerene, is actually adapt only the hapticity to fashion. It always like a simple olefin. And if you look at the nature, it always from MCP model. It clearly indicate that your fullerenes are have a highly electron withdrawing nature. Even if you say, I have an example, you have a C carbon-carbon double bond, it's up to the tetracyano. Tetracyano. If you're asking for the DCD model, this will have only 90% of MCP model. Tetracyano, highly electron group, but your fullerene with a metal compound, the hapticity 2, this is actually 98% of your MCP model. That clearly indicate that your fullerene is a very powerful electron withdrawing nature. Therefore, in all the cases, I think I go back again, look at in all the cases, your fullerene actually adapt the MCP model, not the DCT model. That clearly indicates the electron cloud nature. Very rarely, your fullerene ligand may adapt a hapticity 5 or hapticity 6, but generally this is correct. Hapticity 2 is actually the ligand, and these are the example for a fullerene. And this is a very rare example. You could be able to see hapticity 5. Yeah, hapticity 5, very rarely it will adapt. So that's all. That's all about the various different type of ligand which actually are dominating the organometallic chemistry. As I said in the beginning, though we said transition metal organometallic compound, if you go back and see what we studied is the ligand, because in this case the ligand is the one is actually going to decide all the property of the complex. Therefore, tuning either through sterically or electronically, we could be able to alter the property, whereas the metal remains kind of a simple as a kind of a Lewis acid. It has some effect, but that is not dominated, and therefore that's the reason we studied organometallic chemistry in terms of from its ligand behavior. That actually comes to an end for the organometallic, the basic concept where we mainly focusing only on the ligands. Okay, ஏன்னா இங்க எல்லா மெட்டலுமே கிட்டத்தட்ட ஒரே மாதிரி தான் ரியாக்டிவ் காமிக்க போகுது. ஆமே அட்லீஸ்ட் லைக் குரூப் வைஸ் நிக்கல், பேலடியம், பிளாட்டினம், கோபால்ட், ரோடியம், ரேடியம் எல்லாமே அந்த மாதிரி ஃபார்ம் போகுது. therefore the ligand is the one we always think. Okay, therefore எப்பவுமே நான் ஜென்ரலா என்ன சொல்லுவோம் அப்படின்னா, when talk about the inorganic chemistry, the properties of the ligand will actually affect the properties of the metal complex, which in turn affect the application. This is the link. அப்ப என்ன அர்த்தம் அப்படின்னா நான் லிகாண்ட்ல ஏதாவது சின்ன சேஞ்ச் பண்ணா கூட என்ன ஆகுன்னா, இட்ல அஃபெக்ட் தி மெட்டல் காம்ப்ளெக்ஸ் ப்ராப்பர்ட்டிஸ் ஆஃப் த மெட்டல் காம்ப்ளெக்ஸ் which in turn affect the application. அதுதான் இங்க காரணம். That is one reason we still doing a lot of research with the metal complex. சின்ன சின்ன சேஞ்ச் தான். ஃபார் எக்ஸாம்பிள், அமோனியாக்கு பதில் எத்திலின் டைமின் போட்டாலும் சின்ன சின்ன பாஸ்பரஸ் எடுத்து நான் PH3க்கு பதில் P methyl trice போட்டா கூட the property of the complex will be varying. பார்க்கறதுக்கு ஒண்ணுமே கிடையாது. ஹைட்ரஜன் மெத்தில் ரெண்டுமே பெரிய டிஃபரன்ஸ் கிடையாது. எலக்ட்ரோநெகட்டிவிட்டி இல்ல எலக்ட்ரான் பெரிய டிஃபரன்ஸ் கிடையாது. பட் இட் வில் இம்பாக்ட் even a very small change in the ligand character will affect the metal, which in turn affect the application, and that is how we are doing. Okay, so I hope you could able to follow the most of the thing. அப்ப organometallicsனாலே மொத்தம் 3 கான்செப்ட் தான்: 18 எலக்ட்ரான், pi back bonding and the MO diagram approach. அப்ப எந்த இடத்துல எந்த கான்செப்டை யூஸ் பண்ணுங்கிறத தெளிவா பார்த்து புரிஞ்சுட்டோம் அப்படின்னா, it is very much easy to score a very good one. எல்லா क्वेश्चन எந்த क्वेश्चन எப்படி கேட்டாலுமே நம்மளால ஆன்சர் பண்ண முடியும். Is it clear? Any doubt? டவுட் இருக்காப்பா? டவுட் இருக்காப்பா? Yeah, is there? Can you hear me?
Yes, sir.
Okay, fine. See, பாடம் நடத்தியாச்சு. Now it's up to you. நீங்க தான் you have to take the correct book and try to solve as many as
question as possible, including QE. ரொம்ப ஸ்டாண்டர்டான புக் QE, the Miesel and Tar, the E. Catherine Housecraft, D.D. Gupta, A.J. Lass, இந்த புக்ஸ் இருக்க எல்லா ப்ராப்ளத்தையும் எடுத்து ஒர்க் அவுட் பண்ணீங்க. இஃப் யூ ஹேவ் எனி ப்ராப்ளம் bring to me, I will try to help you. ப்ராக்டிஸ் இப்போ நம்ம எல்லாமே எவ்ரி டைம் ஆர்கனோமெட்டாலிக்ஸ் வந்து ஒரு 4 to 6 மார்க் கொஸ்டின் கேட்டுட்டே இருக்காங்க. we need to grab that 4 to 6 மார்க். ரொம்ப அதான். ஸோ therefore we need to solve it. அது எப்படி நடக்கும்னா how you are approaching, நீங்க எப்படி இந்த அப்ரோச் கொண்டு வரீங்கிறது தான் இங்க முக்கியமானது. அண்ட் ஐ ஆல்ரெடி ஷேர் தி பவர் பாயிண்ட் வித் த பீப்புள் ஹூ ஆர் ஆஸ், யாராவது கேட்டீங்கன்னா அவங்களாம் நான் ஷேர் பண்ணிட்டேன். அது கொஞ்சம் டீடைல்டா இருக்கும். இதுல நம்ம வந்து கண்டென்ஸ்டு வெர்ஷனா ரொம்ப லிமிட்டட் அங்கே எக்ஸ்பிளைன் பண்ணியிருப்போம். அங்கே இன்னும் டீடைல்டா இருக்கும். யூ கோ த்ரூ தி பவர் பாயிண்ட் இன் ஃபுல் டீடைல்டு மேனர். இஃப் யூ நாட் அண்டர்ஸ்டாண்டிங் எனி திங், யூ ஆல்வேஸ் பிரிங் டு மீ, ஐ வில் ட்ரை டு ஆன்சர் இட். வேற ஏதாவது இருக்கப்பா டவுட்டு? Okay, if no more doubt, please. Otherwise, if doubt இருந்தா கூட அப்ப later கேட்டுக்கோங்க. I will stop here. Maybe after a couple of time, we'll take the organometallics reaction mechanism and then application in catalysis we'll take. Okay. Thank you. Thanks so much.